Hi again. In this video we will present some of the main steps in hybridization of powertrains from mild hybrids to full electric vehicles. There are many different ways to build hybrid powertrains, so there may be hybrids which does not fall into any of the described categories. However, at present, 2018, these seems to be the main hybrids now and also for the next generation of cars. We have chosen to discuss these categories of hybrids since they are suitable for different market conditions regarding the buyer's preferences, incentives, and the industry's prerequisites. The power levels and battery sizes we give in the examples are typical for cars. Of course, similar categories of hybrids can also be used in other vehicles, but the sizing of the components can then be rather different. Each of these hybrids will be explained in detail later in the course. This first presentation is only intended to give an overview, such that it's clear why they are sized differently and what demands they aimed to meet. We start with the conventional gasoline combustion engine powertrain as a reference. The investigated vehicle is a mass-market family car with an engine power of 100 kilowatt. The combustion engine powertrain may have a system to start and stop the engine at standstill. This has sometimes been called a microhybrid, but has become so common on some markets that it's not called anything special. This powertrain cannot recuperate braking energy and has no capability to drive electrically or to charge energy from the electric grid. Since the combustion engine is the only power source, the maximum traction power is 100 kilowatt. The fuel consumption we set to 100% and use as a reference when comparing with the different hybrid powertrains. Stricter fuel consumption standards require the vehicle industry to reduce the average fuel consumption of their cars. However, this development is not primarily driven by the customer's explicit demanding hybrid powertrains. Therefore, the industry focused to meet the required fuel consumption standards at a minimum cost. The most cost-efficient way to do this is often to make a mild hybrid powertrain. The powertrain is based on the standard conventional powertrain with a minimum of modifications. As an added benefit, the mild hybrid system can offer some improvements of performance by using the electric machine to boost the power of the powertrain. Of course, the extra power from the electric machine can just as well allow downsizing the combustion engine while maintaining the performance of the conventional car. Like I said, the mild hybrid is based on a conventional combustion engine powertrain. The engine typically has the same power as the corresponding conventional vehicle, here 100 kilowatt. To reach a fuel consumption that is low enough, the mild hybrid does not have to use all the fuel-saving abilities of hybrids, and therefore is focused on stopping the engine at standstill and regenerating up to about 10 kilowatt of braking power. To save on the hardware, the electric machine cannot be disconnected from the engine, and therefore it's not possible to drive electrically without having the combustion engine running. The mild hybrid only have a very small battery of about 0.5 kilowatt hour, and it cannot be charged from the grid. Using the electric motor to assist the combustion engine, the maximum traction power can be up to 110 kilowatt. The added power and the quick torque response of the electric machine will give the mild hybrid better performance than a conventional vehicle with the same combustion engine. The fuel consumption will be about 90% relative to the conventional vehicle powertrain. If there are stronger incentives for reducing the fuel consumption below what the standards stipulate, or if the customer wants to pay extra for the lower fuel consumption, a full hybrid is the next hybridization step. Compared to the mild hybrid, it has a bigger electric machine, sized to be able to recuperate almost all braking energy. The powertrain is also built in a way that the electric machine can propel the vehicle by itself when the power demand is low. Of course, this gives the opportunity to sometimes switch off the combustion engine while driving. A stronger electric machine will offer more performance improvements than the mild hybrid, or a stronger electric machine means that the combustion engine can be downsized even more. More fuel can be saved compared to the mild hybrid, but even if the electric machine is increased in power, there is a limit for how much fuel can be saved. In normal mixed driving, it's difficult to cost-effectively reduce the fuel consumption more than 25 to 30% compared to the conventional powertrain. The full hybrid has an electric machine and battery which can recuperate about 25 kilowatt. That power can also be used for all-electric traction. Note that some full hybrids like Toyota Prius has a much greater electric machine power rating, but that power is used as a part of the electric continuously variable transmission. The power for recuperation is still in the order of 25 kilowatt in this case. A full hybrid cannot be charged from the grid, and it has a battery capacity in the order of 1.5 kilowatt-hour. Using the electric machine for boosting, the maximum traction power can be up to 125 kilowatt. A full hybrid typically consumes 75% of the fuel compared to a conventional powertrain. Some countries have strong incentives for ultra-low fuel consumption, lower than what can be reached by a full hybrid, and then a plug-in hybrid can offer this at a reasonable cost. Customers who are prepared to pay extra to drive fully electric is also another target niche for the plug-in hybrid powertrain. The plug-in hybrid powertrain has a bigger electric machine than the full hybrid to allow for driving fully electric with the basic performance. The battery is typically sized for about 50 km all-electric drive, since that is sufficient for most trips with a typical car. To keep hardware cost low, the powertrain is often based on a conventional combustion engine powertrain, but it requires several new components. The high power of the electric machine offers very high performance when the electric machine is used in combination with the combustion engine. The power of the electric machine is in the order of 50 kilowatt to allow all electric drive in most normal driving situations, and that also allows for high power recuperation. Of course, being able to charge from the electric grid is the main characteristic of a plug-in hybrid. And to be able to bring significant energy and still keep the cost low, the battery capacity is typically about 10 kilowatt-hour. A combined traction power of 150 kilowatt is possible, which provides a big performance increase over the conventional powertrain. The fuel consumption of a plug-in hybrid depends on trip lengths, but is typically about 25 to 50% of the conventional powertrain. If sufficient incentives are directed towards fully electric vehicles, or customers are prepared to pay extra for such vehicles, the plug-in hybrid will get a competitor in the battery electric vehicle with range extender. This is a vehicle with full performance in all-electric mode. The range extender is only added to charge the battery when it runs out, in the case there is no access to public chargers. The battery electric vehicle with the range extender may from the outside look very similar to the plug-in hybrid, since they both can drive fully electric. When the battery is empty, they can both continue to drive using a combustion engine. But looking under the hood, they are often quite different. The plug-in hybrid is typically based on a conventional powertrain adding an electric machine and battery to allow some fully electric drive at a low cost. This leads to limited size of the electric components. In demanding driving situations, it's likely that the combustion engine needs to be turned on, even if the battery is not yet empty. The battery electric vehicle with range extender is typically a vehicle designed to operate as a fully electric vehicle, with powerful electric machine and a big battery, which can deliver high power for a long time. The only time the range extender needs to be started is when the battery is empty. Typically, the range extender vehicle also has a bigger battery than the plug-in hybrid. To save money and space, the power of the range extender is limited, such that it can only provide the average power needed for long trips. Even when running on the range extender, the battery will have to supply the power for a short time during accelerations and later be charged again by the range extender. Compared to a battery electric vehicle without range extender, the battery can be made a little smaller, both to make room for the range extender and to compensate for the added cost of the range extender. The range extender power is only in the order of 25 kilowatt, which is sufficient to allow for long-range highway driving. It has all the same functions as the plug-in hybrid, but a higher power of the electric machine, about 100 kilowatt. The battery is typically bigger than in the plug-in hybrid, at least 20 kilowatt-hour, to provide the higher power to the electric machine, but also to have longer all-electric driving range. Due to the bigger battery and the higher power of the electric machine, the range extender vehicle typically drives much more on electric energy from the grid than the plug-in hybrid. This leads to a very low fuel consumption in the order of only 10% of that of the conventional powertrain. The actual fuel consumption, of course, depends strongly on trip lengths and how often the battery is charged from the grid. Finally, we get to the battery electric vehicle without a range extender. This is not a hybrid vehicle and is, just like the conventional vehicle, included as a reference. In this type of vehicle, the electric machine is of course sized for full performance. If there is a comprehensive fast charging infrastructure available at a reasonable cost, the battery electric vehicle will be a strong competitor to the range extender vehicles. Since high-power fast charging has become possible, it does not need to take a lot of extra time to charge, and eliminating the range extender will save some cost and free up space in the vehicle for other use. The battery electric vehicle without range extender has the same electric machine power, 100 kilowatt. The battery can have the same capacity as the vehicle with range extender, but is often bigger than 30 kilowatt-hour. Of course, the fuel consumption will be zero for this vehicle, since all the energy comes from the electric grid. Now we have an overview of some important types of vehicles, from a conventional combustion engine vehicle to a battery electric vehicle with no combustion engine at all. In the table we see a stepwise hybridization, and we can readily compare them, the relative fuel consumption, for example. There are of course more possible sizes and concepts than presented in this table, but these steps are interesting as they connect to different incentives, market conditions and buyer demands. So, to summarize, we have seen that the stricter fuel consumption standards, without any particular incentives apart from that, are likely to drive the market in favor of mild hybrids. Where there are extra incentives for reducing fuel consumption below the required fleet average, or buyers are prepared to pay extra for low fuel consumption, the full hybrids are likely. Demands for a vehicle which can drive fully electric a short distance at a low cost will lead to plug-in hybrids. Demands for vehicles which can drive fully electric almost all the time will, if the charging infrastructure is limited, lead to a battery electric vehicle with range extender. And if demands are the same, but with a well-developed charging infrastructure, that will lead to battery electric vehicles. All of these powertrains already exists on the market. As the fuel consumption standard becomes stricter, and if more and more incentives are introduced to reduce fossil fuels, the market is expected to move towards more and more electrified powertrains. How quickly this will happen, and what type of powertrains will get the biggest market shares, is very difficult to predict. They will most likely differ between different countries and regions. Okay, that was an introduction to the different steps in the hybridization of powertrains. Before we look closer at the mild hybrid powertrain, click Next to check what you have learned about the different types of hybrid powertrains.